So let's try these out. This is a sample question. So a satellite with a period of 24 hours, so 24 hours to go um, around the Earth, is positioned 1 kilometer above the Earth's surface. The radius of the Earth is 6.371 million meters, so that's the radius of the Earth. Calculate the mass of the Earth. Well, here's step one. The equation for orbital velocity is equal to gm over r, and the equation for velocity is 2 pi r over t, as long as it's going in a circular pattern. So what we do is we kind of write this out. So v equals, this kind of got messed up a little bit, but v equals square root of gm over r, and v is equal to 2 pi r over t. So we set those equations equal to each other, and we rearrange to solve for mass. This would be the radius, like the distance from the center of the Earth to the center of the satellite. This period would be the time to go around the Earth once, and then this will also be the radius. So we're going to have a radius in two terms, gravitational constant. So we rearrange this up for mass. So what you do is you'd square both sides. Then you would get this on the left-hand side. Square root goes away up to here. What you can do is multiply both sides by r and divide both sides by g. So m would equal this. And then kind of going one step further, when you square this, you can square the whole top. 4 times pi squared times r squared divided by t squared. And then r squared times r is r cubed. So you end up with this equation, 4 pi squared r cubed over g t squared. So plugging in some of these numbers, r would equal 6.371 times 10 to the 6, which is the radius of the Earth. But you would add on that 1,000 meters because it's not on the surface of the Earth. It's actually 1,000 meters or 1 kilometer above the surface. G is a gravitational constant, which I didn't write the units on here, but it's just going to be a number we're going to plug in. The period, if you remember, the period of the orbit was 24 hours. So I'm going to convert it to seconds because we want our answer in all these are SI units when you use it, so make sure that you use SI-based units. And so when you plug in this for R, this for G, and this for T, you get the mass of the Earth, which is actually correct, 5.97 times 10 to the 24th kilograms. All right, second problem. Let's say we fire alpha particles, which is just a helium nucleus, at a gold atom. So this is called the Rutherford experiment, where they tried to figure out like the size of different atoms, different nuclei. So what you do is you fire alpha particles into like a gold foil, and you detect it on this other detector, like with voltages and intensity and things like that. But anyway, so back to this. The nucleus of the gold atom will repel the alpha particle because the nucleus is positively charged, alpha particle is particle charged. So they're going to repel. How close together can they get? So you can imagine that an alpha particle is going to come in here at really, really fast speeds. Basically, this whole thing is vacuum, so it doesn't collide with anything else. And what they do is they shoot this out as fast as they can, basically near the speed of light. And we'll just assume it's going to speed of light. Technically, it can't go to speed of light, but we're going to assume it does as fast as it can. And once it hits this foil, it's going to scatter because it's going to basically get repelled and bounced off. And based off the scattering, they can determine the size of the nuclei inside of this. Now, this is also, you can think about as diffraction too. You're sending a wave of particles in, and it's hitting a bunch of waves, and it's going to produce an interference pattern back here. You can also think of it that way. That's like the wave-particle duality of matter. So you can think of it as like particles that are hitting this and like repelling and scattering at different angles. Or you can think of it as a wave going through these tiny little openings and making a diffraction pattern. Either way, you get the right answer, which is kind of cool. Now, in the next video, I'll go through the math of how to actually calculate this, and that'll be the final video for this nuclear / fields physics little mini unit here. So stay tuned for that.